Good day, I'm Maile Matsiba. Welcome back to our channel. Today we're continuing with the last part, which is part 5 of our semester test 2 of 2015 of our CIR 123, which is the second chemical engineering module at the University of Pretoria. We are looking at question 2 of the semester test and number B of this question 2. It says the exhaust gas from a reactor flows in a 3-inch diameter, 3-inch inside diameter pipe. The pressure is 120 kilopascals Gauss and the temperature is 540 degrees Franken. The atmospheric pressure is 650 millimeters mercury. The linear velocity of flow is 6.53 meters per second. Now the question says calculate the degree of completion of the reaction. Now with the degree of completion of reaction, we know that already in question A of this same question, we did calculate the mole analysis of the feed stream. Now when they ask for the degree of completion of the reaction, it's important to note that we need to then find the mole analysis of the exhaust gas, and then we're going to be doing comparison and then to use the mole analysis of the feed stream and the mole analysis of the exhaust gas to find out or to calculate the degree of completion. So the first steps to do is, if we can check here, we have some values that we're going to need to use, but they're not in the units that we would love. So they're not in SI. For instance, we have 540 degrees Franken and 650 millimeters mercury. So the first thing to do is for us to convert all these other values into SI units, and that is exactly what we're going to be doing. So, but just to give it make much more sense, we know that absolute pressure is equals to gauge pressure plus atmospheric pressure. So we need absolute pressure, and the absolute pressure is equal to the gauge pressure plus the atmospheric pressure. So, and we know that the gauge pressure has been given as 120 kilopascals gauge, so it's an S size, no problem. But our atmospheric pressure, it's actually 650 millimeters mercury. So we're going to need to do some conversions there. So we can just say that atmospheric pressure is equal to 650 millimeters mercury multiplied by the conversion unit is 101.325 kilopascals all over 760 millimeters mercury, right? And if you do your calculation there, you find that the atmospheric pressure is actually 86.66 kilopascals. So we then know for sure that if the atmospheric pressure is that, and then therefore the absolute pressure is equals to 120, which is the gauge pressure, plus 86.66 kilopascals. Let me put kilopascals here, right? And then if you use your calculator, it gives you 206.66 kilopascals. So then we go to the temperature. We know the temperature is equals to 540 degrees Franken, and converting that to Kelvin, we can just divide by 1.8. So we can say divide by 1.8, and that will give us 300 Kelvin. So yeah, so that's how it's going to be. Or if I can just put in the units here, I can just say degrees Franken per Kelvin, right? Yeah, so that's going to give us 300 Kelvin. So, and also we can just check out, okay, before I go there, let me just bring a little bit more of light into this to see why are we really bringing this forth. Remember, we need the mole analysis of the exhaust gas, and at this moment we don't really have as much information, but we can actually use all this information here to calculate the total number of moles of the exhaust gas using the equation PV equals to N RT, and then saying N equals to PV over RT. So with that, we can actually be able to calculate the number of moles of the exhaust gas. Though we don't really know the composition or the analysis of the exhaust gas, but we can calculate the total number of moles using this equation. And with that, we need the pressure, the volume, R we know, and then we need the temperature. So far, we have the temperature and the pressure. Well, the R is a constant, and now we also need the volume. So for us to get the volume, it's a little bit tricky, but it's not so difficult. We just need to convert the inside diameter from inches to centimeters, and if we're doing that, we can just say diameter is equals to 3 inch multiplied by 0.0254 meters. Yeah, it's meters all over 1 inch, and if you use your calculator, that gives you 0.0762 meters. So this is actually our inside diameter, and yeah, it will be easier to use with a to use a radius. So we can always say, therefore, radius is equals to diameter all over 2, which then is equals to 0.0762 meters all over 2. And if you use your calculator, it gives you 0.0381 meters. So this is going to help us to actually calculate the volume so that we can be able to use it in this equation. However, the volume will not be, it's easy to calculate it, just that I need to explain something about it. We're going to be using the velocity of flow here of 6.53 meters per second. So we are told that for every second, the velocity of the flue gas, or rather the exhaust gas, is 6.53 meters. So we can just visualize that and say, where do I put it? Let me write it here. Let's say this is actually the pipe, right? And this is a distance of, or the length of 6.53 meters, right? So we can use this principle to actually calculate the volume. But remember, it's 6.53 meters per second, which means for every second, the pipe fills up this, right? And this becomes a diameter of 0.0762 meters, or the radius, you can divide that by half. So with that said, it means that if we have the length and we also have the radius, we can be able to calculate the volume, right? However, it's important because now this is actually a linear velocity of the pipe is not 6.53 meters, but we can actually focus, for us to be able to get the volume, we can actually focus on 6.53 meters, right? And then calculate that volume in terms of, rather, per second or per time. In this case, it's going to be per second. I hope that's much clearer. We all know that the pipe is actually much bigger, right? It's much bigger. It should be much bigger. But for us to be able to calculate the volume, we can actually use the principle of understanding that if this gas travels 6.53 meters, right, per second, and we have that we know the diameter is 0.0762 meters, then we can actually get the volume per second. Though we don't really get the volume of the whole pipe, but we know how much volume per second. And that's the principle we're going to be using. So we're going to be just saying that V is equals to pi r squared L, right? L for the length. And understand the length in these terms, it's actually is the linear velocity of flow, right? So we can just say equals to pi multiplied by our radius, we know, is 0.0381, right? Multiply our length is 6.53, right? it's important when we're going to be calculating this volume to understand that it's going to be per second. Why? Because our length is actually the linear velocity of flow. So it's equals to, if you use your calculator, you're going to be getting 0.0297792 meters cubed per second. So that's basically the same principle. So now we're having the linear velocity of flow, and then we use the diameter to get the volumetric flow per second. Now it's wiser, we have it per second, it's wiser to convert this per hour, because in our original problem statement of question 2 of this semester test, they actually gave us the feed gas as kilograms per hour. So it's always wiser to convert the volumetric flow to hours, and when we do that, we can just say therefore V is equals to 0.0297792 meters cubed per second multiplied by 3,600 seconds, right, all over 1 hour. And if you use your calculator, you get 107.20512 meters cubed per hour. So now we know the volumetric flow rate, that it's actually 107.20512 meters cubed per hour. We don't know how much of the number of moles yet, but we know that the total moles are actually moving at the volumetric flow rate of the exhaust gas is actually 107.20512 meters cubed per hour. And if we have that, we can go back to the equation to say N is equal to PV over RT. Yes, we can then use this to calculate the number of moles also per hour, though we won't really know the actual mole analysis of the exhaust gas, but we'll know the total amount of, this will help us get the total amount of moles. So now with that said, okay, let me say therefore N is equals to, our pressure we calculated to be 206.66 kilopascals, right, multiplied by, this is our volume, is 107.20512, right, meters cubed per hour, all over our R, it's actually 8.314, right? Excuse me, I'll leave it like that without the units. And our temperature is 300 Kelvin, right? So when you do that, then you get that therefore the number of moles is equals to 8.882612 kilomole per hour. So the total number of moles of the exhaust gas is actually 8.882612 kilomole per hour, right? So that actually is an important step towards solving this actual problem. And with that said, then this takes us then to another important step. Well, it's taking us to an important step that is going to help us to actually get the mole analysis of this total number of moles. So remember the equation of the reaction was, or is, CH4, right? And then you get CO plus 3H2, right? So we know actually this is the reaction equation. So an important or an easy approach to solve this is that we're going to need to find how much. Remember, at this moment we know what was in the feed gas. We know how much of H2O was there, we know how much of CH4 was there, right? And obviously there wasn't CO, and there was also no hydrogen. So now at the exhaust gas, we want to know how much of H2O is left and how much of CH4 is left, and also how much of CO formed and also how much of H2 has formed. But for us to get that, we're going to need, in principle, to know how much of the limiting reactant has actually reacted. And in this case, from our question A, we know already that our CH4 is actually the limiting reactant, and we need to know how much of that reacted. So with that said, we're going to say let X be the number of moles of CH4 that reacted, right? So this is actually an important step. We don't know how much of the limiting reactant or CH4 reacted, but we define that as X. And from there, we're going to be figuring out everything else that reacted and that formed in terms of X using that. So now we know that the ratio of, let me write here that the ratio of H2O and CH4 is 1:1, right? Therefore, if X kilomole of CH4 reacted, therefore H2O reacted is equals to X kilomole, right? Let me call this not just X but X kilomole. So it's X, let X kilomole be the number of moles of CH4 that reacted. So if X kilomole of CH4 reacted, then X kilomole of H2 reacted. And in that same light, let's go to the CO. The ratio of CH4 and CO is 1:1. Therefore, CO produced is equals to X kilomole, right? Therefore, CO produced is actually X kilomole, right? Now, in the same light, we can go to the hydrogen and say the ratio of CH4 and H2 is 1:3. Therefore, H2 produced is equals to 3 times X kilomole is equals to 3x kilomole. So this is actually the principle. So now we know how much of H2O reacted in terms of X, also how much of CH4 reacted, and also how much of CO and how much of H2 did form. So, but we have that in terms of X. This moved us then to our following step, because remember I've mentioned that in question A we already figured out or calculated how much was in the how much of H2O and CH4 was in the feed gas. So if this much of H2O and CH4 did react, then we can actually calculate how much of H2O and how much of CH4 are left in the exhaust gas after the reaction. So, and we'll get that in terms of X. So this takes us to another important step. So in this step, we'll say that after the reaction in the exhaust gas, now this is the actual analysis in terms of X in the exhaust gas after the reaction. We know that CH4 is equals to the CH4 that was in the feed gas minus the CH4 that has reacted, and we know that the CH4 that was in the feed gas or in the feed stream was 2.3350 kilomole, right? 2.3350 kilomole, right? Minus X kilomole, which is the number of moles of CH4 that has reacted. And in the same light, H2O is equals to 3.0355 kilomole minus X kilomole, right? And then CO produced is equals to X kilomole, right? And H2 produced is equals to 3x kilomole. So this is actually the exhaust gas. But let's also remember that from our question A, we can remember that there was actually nitrogen that was in the feed gas, or in the feed stream that was in it. So we also know that the N2 that we did calculate it in question A as 0.2857 kilomole. And I need to put this everything of this per hour, right? This is per hour. So this is actually the analysis of this is actually every single gas in the exhaust gas after the reaction. So I can just add up this whole thing and say, therefore, total kilomole of exhaust gas is equals to 2.335 kilomole minus X kilomole minus 3.0, let me put it here, plus 3.0355 kilomole minus X, right? And then plus X kilomole, right? Plus 3x kilomole plus 0.28571 kilomole. So if you do the simplification there and you add up everything there, you'll find that the total kilomole of exhaust gas is actually equals to 5.65621 kilomole, 5.65621 kilomole minus 2x kilomole. So this is actually a simplified version of this when I added up and subtracted the x's. So now if we know that this is actually the total kilomole of the exhaust gas, we can actually remember that we did just calculate not a long time ago. Where's that question? We did calculate how much of, where was that? We calculated how much was the total kilomole in the exhaust gas. Oh, here is it. We did calculate that the number of moles of the total exhaust gas was 8.882612 kilomole per hour. But we didn't have the total analysis. But here we also know that this is actually the same thing. Or can I say per hour? This is actually this is the total kilomole of the exhaust gas, right? And also this is the total kilomole of the exhaust gas. So we can actually equate this to this and solve for x. We can say therefore 5.65621 kilomole per hour minus 2x kilomole per hour is equals to 8.882612 kilomole per hour. Now, with that said, we can simply do the rearranging and the simplification, and we can find that 2x is equals to 8.882612 kilomole minus 5.65621 kilomole. Well, this is per hour, this is also per hour, right? Therefore, our X is equals to 1.613201 kilomole per hour. So now we find out, we managed to actually solve for X. We know that our X is 1.613201 kilomole per hour. And with that said, then this moves us to, this moves us to another important step here. Let me just bring what's the reaction equation? I want the equation where I put, so this is actually the reaction equation, right? This is actually the reaction equation. So now if we know what X is, we know how much of CH4 reacted, right? And if we're actually asked to calculate the mole analysis of the exhaust gas, we'll go further, just plugging in X in all the other values and then finding it out. But now the question, they say calculate the degree of completion. So with the degree of completion, we can simply just find out how the limiting, we know already that the limiting reactant is actually CH4. So we can actually use CH4 and CO and use that to calculate, use that as a basis to calculate the degree of completion. And with that said, we can just say, we know that, let's start with the C. We know that CH4 charged, we know that CH4 charged in the feed stream, right? Charged in feed stream, right? Was equals to 2.3350 kilomole per hour. This was the CH4 that was actually charged, right? And now with this, if this is actually the case, then we can actually then calculate so okay, let me say, if we know that the CH4, this is actually the amount of CH4 that was charged, then we can actually use that and to relate it to the CO and see how much was, what is the CO that was theoretically possible. And we know that the ratio of CH4, the ratio of CH4 and CO is 1:1. Therefore, CO theoretically possible is equals to, all of this is equals to 2.3350 kilomole per hour, right? However, we know that CO that was produced, we know that, let me say, but CO produced is equals to the X, which was equals to 1.61 1.613201 kilomole per hour. Now, with that said, then we can simply go to the degree of completion and say, therefore, let me put something underneath here. Therefore, the degree of completion of the reaction is equals to 1.613201 kilomole per hour, which was the actual production of CO, all over 2.3350 kilomole per hour, which is the theoretically possible, which is the CO that was theoretically possible, multiplied by 100%, right? And if you use your calculator, this gives you 69.087%. So this is actually the degree of completion of the reaction, and this brings us to the end of our semester test 2 of 2015. So thank you for your time. I hope we meet again in our next video.